Welcome back to another stats lecture. In this video, we will be discussing relative measures of dispersion. To kind of link this up with the things that we've talked about so far, we've discussed measures of center, mean, median, and mode, and then after we discussed those measures of center, which we were computing from raw data, we talked about how we could compute those measures of center for grouped data. And so after we talked about that, then we talked about measures of dispersion. And the primary measures of dispersion we discussed were the standard deviation, the interquartile range, or IQR for short, and the index of qualitative variation, or IQV for short. And we talked about when each one of those is useful to look at as we're trying to describe the dispersion in a data set. Now, if we're following the pattern that we followed for the measures of center, you might expect us to take some time now and talk about how to compute measures of center or measures of dispersion from grouped data. But the reality of the situation is that we already know we have a feeling for how spread out a data set is by just kind of simply looking at it. We could go through the effort of trying to figure out what the exact numbers are for how much dispersion there is in a data set by looking at a graph, but I just don't think that that's super important, and so we're not going to spend a lot of time doing that. What we do need to talk about, though, are relative measures of dispersion, because if we want to compare two data sets to say which one of them has more variety, we need to be careful about distinguishing between the absolute amount of variety in a data set and the relative amount of variety in a data set relative to the size of the individuals in the data set. So that's what this section is all about, and hopefully it'll become more clear to you as we move through it why this matters, okay? So make sure your notes are printed, make sure you have the data set for section 1.9 downloaded and ready to follow along, and let's get to it. Okay, so let's talk about relative measures of dispersion. Note that when two data sets have the same mean, then we can compare their standard deviations, and that will tell us which data set has more variation. Or we could state that the opposite way, and it'll tell us which data set is more consistent. However, if we want to compare the dispersion in data sets with different means, then we need to compare their standard deviations relative to their corresponding means. And to see why, consider the weights of dogs and African elephants. I think that if you consider these two different species, right, dogs and African elephants, you would agree that there's more variety amongst dogs, right? There are tons of different dog breeds, right? And so you have some very, very small dogs, and you have some very, very large dogs. Whereas African elephants, there's not much variety there. They're all just very large animals. There aren't a whole bunch of different breeds of African elephant. So I think we would probably want to say that dogs have more weight variety, okay? But the issue is that if you look at their absolute weight variety, the standard deviation for the two groups, you'll see that elephants have a larger standard deviation, right? So dogs have an average weight of 40 pounds with a standard deviation of 20 pounds, while the elephants have an average weight of 12,000 pounds with a standard deviation of 1,000 pounds. Now, obviously 1,000 is much larger than 20, and so you might look at that and say, okay, so obviously there's much more dispersion among the elephants, right? Elephants have a larger standard deviation, and therefore they have more variation in their data. And that's true in absolute terms, but it goes against our intuition that dogs have more weight variety because there are so many different breeds of dog, right? And so you have very small dogs and very large dogs. And so what's going on here is that elephants are just very large animals to begin with. And so 1,000 pounds is not that much relative to their average size of 12,000 pounds, right? Notice that with dogs, their standard deviation is half as large as their average weight, whereas with elephants it's just a small fraction of their average weight. And so this is what we really want to describe when we're trying to compare two data sets. We want to look at, not just their standard deviation, but how large is their standard deviation relative to their average size, okay? And that'll give us a better understanding of which data set has more dispersion in it. So for the standard deviation, the relative measure of dispersion, the corresponding relative measure of dispersion is called the coefficient of variation, okay? So let's talk about the coefficient of variation, or we'll call it the CV for short. So the coefficient of variation is just the standard deviation divided by the mean, okay? So if you're dealing with population data, then it would be computed this way. If you're dealing with sample data, it would be computed this way, all right? So for the population, it's sigma divided by mu. For the sample, it's S divided by X bar. Now, Excel does not have a built-in function for computing the coefficient of variation, so we'll just have to compute the mean and the standard deviation in Excel and then perform the rest of the calculation by hand. Or we could use Excel to do it, but it doesn't have a built-in function. We could also just use a calculator, okay? So let's take a look at that example, dogs versus elephants, okay? So dogs have an average weight of 40 pounds with a standard deviation of 20 pounds. African elephants have an average weight of 12,000 pounds with a standard deviation of 1,000 pounds. Which species has more absolute weight variety, and which species has more relative weight variety? Well, we've answered that first question already, but let's write it down, okay? So we can just say this. We'll say elephants have more absolute weight variety since the standard deviation for elephants, maybe I'll just call that sigma sub e for elephants, is 1,000, which is much larger than the standard deviation for dogs, which maybe I'll call sigma sub d for dogs, right? Their standard deviation was only 20. Okay, so obviously elephants have more absolute weight variety, but which species has more relative weight variety? Okay, for that we would have to compute the coefficient of variation for each group. So for elephants, the coefficient of variation would be sigma divided by mu. Okay, sigma for the elephants and mu for the elephants. That's going to be 1,000 divided by 12,000. I'll pop that into my calculator in a second. Let's do this for dogs as well. So for dogs, the CV is going to be, again, sigma divided by mu, but of course we want to do the standard deviation for dogs divided by the mean for dogs. So for dogs, that's going to be 20 divided by 40. So let's pop those into our calculator and see what we get. So for elephants, it's 1,000 divided by 12,000, and for dogs, it's 20 divided by 40. Okay, so let me write that down. For elephants, I'm going to round, I'm going to say this is approximately 0.083. And for dogs, it was exactly equal to 0.5. Okay. So given this information, we would say, oh wow, so clearly dogs have more relative weight variety. Okay, dogs have more relative weight variety since the CV for dogs is bigger than the CV for elephants. Maybe I should call that CV for dogs and CV for elephants, right? Since the CV for dogs is 0.5, which is much larger than the CV for elephants, right, which is only about 0.083. Okay, so elephants have more absolute weight variety, but dogs have more relative weight variety. And of the two of those, I would say that the relative weight variety makes more sense in this case, if we're just trying to figure out, which animal is, for which animal we would expect to see just a wider variety, right? Clearly it's for dogs than it is for elephants. This time we'll try to compute the coefficient of variation from raw data. In the previous example, the mean and the standard deviation were given to us. Here we'll have to compute those. We'll use Excel to do that. But it says, I tracked the number of hours I slept each night for 19 nights in February when school was in session, and 19 nights in June when school was not in session. I made all this up, by the way. And then the question is, when did I have a more consistent sleep habit? So I want to compare the data from February to the data from June. I want to compare how much variety there is in those data sets. And so to compare the variety in these two data sets, I'm going to compute the coefficient of variation, the CV, for each data set. So to do that, first I'll need to compute the mean and the standard deviation for each data set. So for February, to compute the mean, I'm going to do this in Excel. Oh, this is a sample, right? So I should use X bar. So, so to compute the mean in Excel, I use the function equals average, and then I put my data in there. So we'll head over to Excel in a second and see about how much that is. To compute the standard deviation, I would use standard dev dot s for sample, and then put my data in there. Okay, and I'm going to do the same thing for June. Okay, let's head over to Excel and see what we get. Okay, so I'm just going to click into an empty cell, and to get the mean, I'll say equals, actually let me label these. Maybe I'll make a little chart over here. I want the mean, I want the standard deviation, I want this for both February and for June. Okay, so this will help me keep track of what I'm which numbers represent which statistics, right? So for February, I'm going to say equals average. I'll tab to select that function, and then I'll select my data. Close the parentheses and hit enter. For the standard deviation for February, I'll say equals standard deviation dot s for a sample. Okay, I'll hit tab to select that function, and then I'll click on my data. There's my standard deviation for February. Same thing for June. Equals average. And equals standard deviation dot s. Okay, so that's interesting. It looks like on average I got a little bit less sleep in June than I did in February. In neither month am I getting the full 8 hours of sleep I should be getting, I suppose. But the standard deviation in February was much larger. I wonder if that's true relatively speaking, right? So in absolute terms, right, we would say my sleep habits were more consistent in June. But in relative terms, that may be a different story. To figure that out, we have to compute the CV. So let's write these down, and then we'll compute the CV. So I'm just going to write these down while I have this up so I don't forget. For February, I'm going to say that this is about 6.9. The mean is about 6.9, and the standard deviation is about 2.2. And for June, I'll say that the mean is about 6.6, and the standard deviation is about 1.1. Okay, so now at this point, if I want the CV for each of these, it's going to be S divided by X bar. So in the case of the February data, this would be approximately 6.9 divided by 2.2. And for the June data, it would be approximately 1.1. Ooh, I got these backwards. Let me fix that. It's S divided by X bar, so it would be 2.2 divided by 6.9. Okay, and here it would be 1.1 divided by 6.6. Now at this point, you could you could plug these values into your calculator and see how much that is, or you could just use Excel. Okay, Excel might be a little bit better because Excel will store more digits, right? So instead of rounding to one decimal place, it'll have all of the decimal places in it, which would give you a more accurate answer. So to use Excel now, I can add another row to my little table that I'm making and get the CV. I can say that the CV for February is going to equal the standard deviation for February, so I'll just click on that value, divided by the mean for February, so I'll just click on that value and then say enter. So there's the CV for February. And for June it would be similar. I would say equals standard deviation for June divided by mean for June. Okay. So in absolute terms, I had a more consistent sleep habit in June, and in relative terms, I also had a more consistent sleep habit in June. Let's write these CVs down. So the CV for February is about 0.32, and for June it's about 0.17. Okay. So when did I have a more consistent sleep habit? We would say June, because it's its CV is smaller, okay? Or if you wanted to say, when did I have more variety in my sleep habit? Well, then you would say February, because its CV is larger. Okay, but I was more consistent in June. So I had a more consistent sleep habit in June, because the coefficient of variation for June is smaller than the coefficient of variation for February. Okay, so that's how the coefficient of variation works. One thing that you might be thinking is, okay, so this is how we would compare the amount of variation when we're using standard deviations and means, but that's only appropriate when the data is bell-shaped, right? Or symmetric. What do you do if the data is skewed, right? In that case, you would use the median and the IQR. So what do you do if you're trying to compare IQRs, right? And the answer is, if we want to compare the IQRs of two data sets, excuse me, we would also want to compare them relative to the center of the data set. So the tool that we'll use for this is called the quartile coefficient of variation. So coefficient of variation is standard deviation divided by mean. The quartile coefficient of variation, or QVC for short, is the IQR divided by Q3 plus Q1. If you may recall that the formula for the IQR is Q3 minus Q1. So another way to view this formula is that it's Q3 minus Q1 divided by Q3 plus Q1. So if we just want to describe the amount of variation in a data set that is skewed, we'll use the IQR. But if we want to compare the amount of variation in two data sets and at least one of them is skewed, then we'll compute the QVC, or QCV. Okay. So let's practice this. Here we have two data sets. They represent the weights in pounds of a random sample of soccer players on the left and another random sample of baseball players on the right. Now, before doing any calculations, let's just think about this for a second and use our intuition to see if we can predict who has more consistent weights. So I'll let you think about that. I'm going to go ahead and give you my answer. If you want to pause and think about it, you're welcome to do so. I would say that baseball players, they don't necessarily need to be in super great shape. This might be kind of like a negative stereotype, I guess, but you see some professional baseball players who are not, in super great shape, let's say, right? So it does happen sometimes. Whereas, in order to be a professional soccer player, I think you're pretty much going to have to maintain a slim physique, okay, in order to be competitive. So consequently, there will be some baseball players who, are slim, and others that are a little heavier, right? But soccer players, I think, are going to be a little more consistent with their weights. So that would be my assumption. I would think that so who has more weight variety? I would think baseball players, right? I think baseball players have more weight variety. Okay, part B asks us to create a frequency histogram for each group and identify their shapes, or at least it should say frequency. I'll correct that on your notes before I post them, but let's create a frequency histogram for each group and identify their shapes. Okay, let's head over to Excel to do this. Okay, so our sample sizes are not the same. That's okay. We want a frequency distribution for soccer players. So let's insert a pivot table. I'll do soccer players right here. Let's make sure we're counting the values, not adding them up. So what we want actually is a frequency histogram. I'm sorry if I said distribution. We want a frequency histogram. To get a nice histogram, I think we should probably group the data. Sure, we'll use Excel's suggestion here and see if that gives something nice. That seems pretty good. Okay, and so now I can insert a histogram. I'll select the pivot table and insert a bar chart and get rid of that. Make the bars a little bit larger. So 5%. Okay, so here's a histogram for soccer players. And then let's do this for baseball players as well. So I'll insert another pivot table into the existing worksheet. Let's do this right here. Alright. Again, let's make sure that we're counting the values. And we should probably group into classes here as well. Again, I'll go ahead and take Excel's suggestion. And let's look at a histogram. Okay, and so there's our histogram for baseball players. I think the purpose of looking at these histograms was to try to decide what shape we have going on, what the shape of our distributions are. And I would say, gosh, it's a little bit hard to tell. Maybe if we group differently, we might get a better picture for what the shape would be. But it seems, I would say this one seems kind of skewed right. Okay, and this one seems maybe a little bit more symmetric, but let's try a different grouping. And maybe we can start at 140 and see if that helps. Yeah, okay, so skewed left, okay, for sure. And here, well, 165 is fine. Yeah, I mean, we can change to 160 or something to see if that helps. In any case, this maybe is, so this one is skewed right. This one is skewed right. So the soccer players' data is definitely skewed right. I would say the baseball players, it's still a little bit ambiguous, but probably it seems like they're skewed left. So that's what I would say for those, for the shapes of the distributions. What that means is we're going to want to compare QCVs, right, in order to make this determination about which group has more weight variety. So let's write down our observations so far. So soccer players, the soccer players' data seemed to be skewed right. And the baseball players they seem to be, the baseball players are a little bit less clear. I don't know, we could group by 5s or something and see if that helps. Not really, makes it worse. It's hard to tell. You could maybe say symmetric, or you could maybe say skewed left. So we'll say slightly skewed left. In either case, since the soccer players are definitely skewed right, we're going to have to compare QCVs in order to decide which group has more weight variety. And that's what we're asked to do in Part C, calculate the median, the IQR, and the QCV for each group. So let's do that. Okay, so for the soccer players, to compute the median, we'll use the equals median function. And same for the baseball players. For the IQR, well, the IQR is Q3 minus Q1. And we'll also use Excel to find Q3 and Q1 for each group. So we'll have to go over to Excel to see what those are. Let's maybe do that much, and then we can come back and do the QCV for each group. So let me get rid of these histograms. I think we're done with them for now. So for the median, I'm going to make a little chart like I did before. So we want so we want to compute some values for soccer players and some values for the baseball players. We want the median. We want the IQR, which is going to require us to get Q3 and Q1, and then we can use it to get the IQR. So let's do that much. So for the soccer players, we'll say equals median. I'll select my data and hit enter. Same for the baseball players. Equals median. Select the data. Hit enter. Q3 would be equals quartiles.inc. Select the data, and I want the third quartile. Okay, same for the baseball players. Quartile.inc. Select the data. I want the third quartile. Okay, first quartile equals quartiles.inc. Select the data. And for baseball players, quartile.inc. Select the data. First quartile. Okay. And now finally for the IQR, we would just say equals Q3 minus Q1 equals Q3 minus Q1. Okay, let's write those down. So the median for soccer players was 175. The IQR was 180 minus 160, which equals 20. And for the baseball players, the median was 200, and the IQR was 218.75 minus 190, which comes out to 28.75. Okay. So right off the bat, you can see that baseball players weigh a little bit more than soccer players do on average. And in absolute terms, the baseball players have more weight variety than the soccer players do, okay, because their IQR is larger. But let's look at their QCVs, okay? So the QCV for the soccer players is going to be Q3 plus Q1 over Q3 minus Q1. Or if you want to write that as IQR over Q3, ooh, I got these backwards. I keep doing that today. It's Q3 minus Q1 over Q3 plus Q1. So if you want to write that as IQR divided by Q3 plus Q1, that would also work. Clearly this is going to be 180 minus 160 over 180 plus 160. So we can use a calculator for this, or you could do it in Excel. It's up to you. But let's use a calculator this time. So we'll do 180 minus 160 divided by 180 plus 160. Okay, so there is the QCV for soccer players. So about 0.059. For baseball players, the QCV is Q3 minus Q1 over Q3 plus Q1. That's 218.75 minus 190 over 218.75 plus 190. And again, I'll just use a calculator to figure out how much that is. Well, let me give myself a fraction first. Okay, 218.75 minus 190 over 218.75 plus 190. And there we go. So 0.070. Alright, so we got the median, the IQR, and the QCV for each group. Now the question is, which group has more weight variety? The group that has the larger QCV would be the group with more weight variety, and in this case that's baseball players. So let me try to squeeze it in here. We'll say baseball players have more weight variety. Since they have the larger QCV. Okay. So that's how the QCV works. Let's talk about the index of qualitative variation. Okay, so just to summarize kind of what we've talked about so far, for comparing the spread of two or more numerical symmetric data sets, we compute coefficients of variation, right? CVs. For comparing the spread of two or more numerical skewed data sets, we compute quartile coefficient of variations, right? QCVs. If we want to compare the spread of two or more categorical data sets, we compute IQVs. And you might think, well, we've already talked about the IQV. Don't we have to look at a relative measure of spread? And you're right, we have talked about the IQV, but there's no need for a new statistic here because the IQV is already a relative measure of dispersion, right? It's already relative. So we can just use it to compare the amount of dispersion into qualitative data sets. So I'll just give you one example of that since we've already done this in the past. Okay, but as a reminder, here's the formula for the IQV. Okay, and let's compute the IQV of this data set. We'll compare three groups here. It says the racial composition of 3 states in the United States are given in the table below. So we have race and then the 3 states that we're trying to compare the racial compositions of. We're asked to create a side-by-side relative frequency bar chart for the racial composition in these states. And then we'll compute the IQV for each state and rank the states from least to most racially diverse. Alright, so let's do that. Heading over to Excel. So if I want to insert a side-by-side relative frequency bar chart, this is already a relative frequency distribution. So I can select the table and then go to Insert and Bar Chart. And we can make this a little bit bigger so that we can see the data profile a little bit better. But just looking at this data set, it's really interesting. So the blue bars represent California, the orange bars represent New York, and the green bars represent Wisconsin. In California, I notice a larger proportion of Asian Americans and Latino Americans than in the other 2 states. On the other hand, New York has a larger proportion of Black Americans. So, you know, I think it will be helpful to compute the IQV of each group so that we can determine which one of them has more, which state is more racially diverse. So let's get busy doing that. I don't want to delete that yet because I might want to look at it again later. But let's see if we can compute the IQV of each group. So, looking at California, I'm going to, let's highlight that whole column. We'll copy it and, where should we do this? Let's just do this right here. And I want to do the relative frequency squared, right? So I want to do the proportion squared. So I'm just going to make a, maybe I'll call that the squared proportion. So I'm going to say that this equals this number squared. And then I'm going to click and drag so it does that computation, and then I'm going to add them up. So I'm going to say equals sum okay, I need to do that for New York and Wisconsin as well. So I'm going to copy paste, squared proportions equals this number squared. And then get the total. And then I'll do that for Wisconsin. Alright, so I'm squaring all of my proportions and then I'm adding them up. And the reason that I do this is because that's part of the formula for the IQV, right? We're doing this chunk of the formula for each group, because once we have that, then we can just plug it into this general formula. K, remember, K is the number of categories. So in this case, K is 1, 2, 3, 4, 5, 6. Okay, 6 categories. So we can either do that in Excel or we can do it with a calculator. Probably easier to do this one with a calculator. Okay, so let's do it. So for California, I wonder if I can just copy and paste this number. I'm going to say Control C and Control V. Yeah, so you can copy and paste it if you want. But we're going to have, let me give myself a fraction. We have 6 categories, so K is 6 times 1 minus that sum that we just computed. And then we're going to divide by 6 minus 1. So there's the IQV for California. Let's Control C, and we'll do fraction 6 times 1 minus Control V over 6 minus 1. Okay, so there's the QCV for New York. And then we'll do the same for Wisconsin. So let's Control C, copy that. And then we'll do 6 times 1 minus Control V over 6 minus 1. And there's the QCV for Wisconsin. Okay, so I think we need to write some of these things down. For California, so let me drag this over. Okay, so let's write some of these things down. For California, the QCV, or sorry, the IQV, I've been saying QCV, but I mean IQV, the IQV, we did 6 times 1 minus 0.307 over 6 minus 1, and that comes out to about, let me do it underneath, that comes out to about 0.831. For New York, the IQV was 6 times 1 minus 0.339 divided by 6 minus 1, and that comes out to about 0.793. And for Wisconsin, the IQV was 6 times 1 minus 0.434 divided by 6 minus 1. Okay, and that comes out to about 680 if we're rounding to 3 decimal places. Okay, and that all came from this work here. Okay, so now to answer the question, so we are supposed to rank the states from least to most racially diverse. Well, the least racially diverse state was Wisconsin because it had the smallest IQV, right? And then the next most racially diverse was New York, and then the most racially diverse was California. So least diverse is Wisconsin. Most diverse was California. Okay, and then New York was somewhere in the middle, right? So that would be our ranking. Okay, so as a summary of what we've talked about in this section and putting it together with what we've talked about in other sections, if you're just trying to describe a single data set, okay, if the data set is numerical and symmetric, you would describe the center of that data set with the mean and the spread of that data set with the standard deviation. If the data set is numerical and skewed, you would use the median to describe the center of that data set and the interquartile range to describe the spread of that data set. And if the data set is categorical, then you would use the mode to describe the center of the data set and the IQV to describe the measure of spread of the data set. So that's if you're just trying to describe a single data set. But if you're trying to compare two data sets, okay, then you should compare, if the data sets are both numerical and symmetric, you should compare their means and you should compare their coefficients of variation. Okay? If the data sets are numerical and skewed, you should compare their medians and their quartile coefficients of variation. And if the data sets are categorical, you should compare their modes and their indices of qualitative variation, so their IQVs. Going back to the skewed case, in order for us to, so it's only appropriate to compare means and CVs if both data sets are numerical and symmetric. If at least one of them is skewed, then we should compare the median and the QCV. So that will do it for relative measures of dispersion.